Welcome to the deep dive. Today we are cracking open some really fascinating source material, looking at a challenge that, well, pretty much every pilot faces. High workload, sudden changes right before leaving the gate.
Yeah, the pre-departure crunch time, it's intense.
Mm.
And our sources today, they're a mix, really manufacturer safety insights alongside some pretty critical pilot perspectives.
Mm-hmm.
And they focus on something quite specific, how tiny errors, sometimes just a single digit off in a calculation, often because someone's distracted,
Yeah.
can actually lead to catastrophic failures during takeoff.
The margins are that thin.
They really are.
So that's our mission for this deep dive, understanding these late changes before departure. We'll look at what causes them, we'll dig into two major case studies where small slips had huge consequences, and then explore strategies, both human and tech, to manage it all.
Okay, so let's set the scene. What does this environment actually look like just before takeoff?
Well, the sources describe it almost like an avalanche of disruption. It's not just one thing, it's multiple pressures hitting the crew, often all at the same time.
Right, you've got external stuff like you mentioned.
Yeah.
ATC pushing for an on-time departure.
Exactly. Or ground staff needing a signature, maybe passenger issues filtering up. Then there are environmental changes, sudden thunderstorms, a runway switch, maybe the runway condition changes, wet to dry or vice versa, even a new taxi route just before you expect to move.
And that's just the outside world. Internally, the crew's juggling tasks, maybe dealing with a technical snag, something from the MEL perhaps,
The minimum equipment list? Yeah.
or just the general cognitive load of final checks. Plus, maybe administrative changes pop up.
Ah, yes. The late fuel slip, the updated cargo figures because something changed last minute, or that one final passenger, bags and all, racing to the gate. It feels relentless sometimes.
It does. And here's the crux of it, the real risk. These interruptions often land smack in the middle of critical checklist procedures, especially when pilots are keying data into the flight management system, the FMS. That's when distraction can lead to what the source calls a small, unnoticed but incorrect change. A tiny input error that affects aircraft performance calculations.
Let's make that concrete. Case study 1 really brings us home. This was an accident where the crew was just bombarded with interruptions. Cabin crew questions, radio calls, ground staff popping the door open again, even confusion over the departure procedure, the SID.
Yeah, the workload was immense. And under that pressure, the standard cross-checks just failed. Somehow, the crew entered an aircraft gross weight that was 100 tons lower than the actual weight.
100 tons. That's staggering. But the sources suggest it might have been just, what, a single-digit error? Missing a number, hitting the wrong key?
Quite possibly. It doesn't take much.
Yeah.
Simple typo with massive consequences.
So if the aircraft's computer thinks the plane is 100 tons lighter than it really is, how does that play out on the runway? What's the danger?
Well, it throws off all the performance calculations. The system thinks, okay, light aircraft, less lift needed, so it calculates much lower takeoff speeds. And, critically, it calculates the V speeds incorrectly.
The V speeds. Right, let's quickly define those. V1, VR, V2. What are they telling the pilot?
They're fundamental for takeoff. V1 is the gonna-go speed. Hit an engine failure below V1, you stop. Above V1, you continue the takeoff. It's the maximum speed where you can still safely abort and stop on the runway remaining.
Okay.
VR is rotation speed. That's when the pilot pulls back on the controls to lift the nose, usually aiming for about 3 degrees per second rotation.
Got it.
And V2 is the minimum safe climb speed. You need to reach V2 by the time you're 35 feet above the runway, even with an engine out. It ensures you have enough performance to climb away safely, and they always follow the sequence. V1 is less than or equal to VR, which is less than or equal to V2.
So in this case study, with the weight 100 tons understated, the calculated V speeds were way too low for the actual heavy aircraft. What happens when they reach that incorrect low VR?
The aircraft is simply too heavy to fly at that speed. It doesn't have enough lift. So you get poor rotation, or maybe none at all. In this specific accident, the aircraft essentially refused to lift off properly.
Wow.
They scraped the tail along the runway, a tail strike, and actually lifted off after the runway end, hitting a runway light. They had to firewall the thrust levers, go to full tow GA power to basically salvage the situation and get airborne.
Just barely. And you mentioned something else, too, a related issue with thrust. That low weight input caused another problem.
Yes, the flex temperature calculation. This is really important. Often, pilots use reduced thrust for takeoff to save engine wear, called flex thrust. The FMS calculates how much reduction is possible based on weight, runway length, temperature, etc.
How does it actually reduce the thrust?
It essentially tricks the engines by calculating a higher assumed outside air temperature, the flex temp. A higher temperature means less dense air, so the engine automatically provides less thrust for a given throttle setting.
Okay, I see.
So when the crew entered that weight 100 tons too low, the FMS thought, very light aircraft barely needs any power. It calculated a very high flex temp, maybe 60, 70 degrees Celsius.
Much hotter than reality.
Exactly.
Yeah.
This drastically reduced the thrust available. So they were trying to take off not only with incorrect low speeds, but also with far too little power for the actual heavy weight of the aircraft. It was a double hit.
That's case study 1 then. One massive error triggered by distraction. But case study 2, it shows something different, doesn't it? More like death by 1,000 cuts.
That's a good way to put it. It illustrates the cumulative effect.
Uh-huh.
Several small mistakes, things that might be manageable on their own, they compound. The end result here, the aircraft clipped the tops of trees just after takeoff.
Even though the crew thought they had a clear climb path.
They did. But their calculations, the ones they based that assumption on, were outdated by the time they actually took off. 3 separate factors eroded their safety margin.
Okay, let's peel back those layers. What was the first small error?
It started with the wind. Their performance calculation used 0 wind conditions. But when they actually departed, there was a slight tailwind, about 3.5 knots. Seems tiny, right?
Yeah, very small.
But the analysis showed that alone reduced their potential vertical flight path clearance by 54 feet.
54 feet just from a tiny tailwind. Wow, okay, what was layer number 2?
Runway use. They'd based their numbers on using the full runway length. But operationally, they ended up using an intersection departure, starting 350 meters further down the runway.
So less runway available for the takeoff roll.
Exactly. Which means you lift off later and your initial climb profile is shallower. That cost them another 34 feet of vertical clearance.
So now we're down, what, 88 feet from their expected clearance just from wind and runway position? And they still haven't accounted for the obstacles themselves.
Correct. That was the final critical piece. Their obstacle data, the charts they used, showed 40-foot trees located 655 meters past the runway end.
But that wasn't the reality.
No. The actual trees were taller, 54 feet high, and significantly closer, only 393 meters from the runway end. So you combine that unexpected tailwind, the shorter runway use, and these closer, taller obstacles.
And the calculated safe climb path just wasn't there anymore.
It completely vanished. Moments after getting airborne, their actual flight path took them right through the treetops.
Chilling. Okay, this brings us to solutions. And this is where the source material, particularly the pilot perspective from Captain Peter Krupa, gets really practical. He argues trying to prevent disruptions is futile, like tilting at windmills, he says.
That's such a key insight. You can tell people not to bother you, close the cockpit door, but the phone will ring, the ground agent will knock, disruption will happen. So the focus has to shift from trying to avoid it to actively managing it when it occurs.
Which leads straight into the first big strategy they recommend, task segmentation, or packaging. Basically, break down big jobs into small, manageable chunks. Why is that so effective?
Think about checking the FMS setup. It might involve multiple pages, lots of data entry. If you try to do it all in one term, go and get interrupted halfway through.
You lose your place. Forget what you checked.
Exactly. You might have to start the whole process over to be safe. But if you package it, say, check the performance page completely, confirm it, then answer the radio call, then move to the next page, you protect the integrity of the work you've already done. The interruption doesn't corrupt the whole task.
It compartmentalizes the risk. That makes a lot of sense, actually, for any complex task under pressure.
Definitely.
The second strategy tackles time pressure directly. The source actually gives that human tendency to rush a name. FO, haste makes waste.
Yes. It captures that paradox, doesn't it? When we feel rushed, our instinct is to speed up our actions. But the argument is we all have a sort of cognitive design speed. Try to operate faster than that.
And errors increase.
Not just increase, they increase exponentially. So rushing actually makes things slower in the long run because you're making mistakes you then have to catch and fix. And it makes things much more dangerous.
So the advice is completely counterintuitive. Take your time and slow down when you are in a hurry. The pilots need to set the pace, not be driven by the clock.
Precisely. They are the pacemakers. And this whole philosophy of managing pace and disruption, it kind of crystallizes at one key moment, going off blocks, pushing back from the gate.
That's the boundary line.
That's the line in the sand, according to the source. The chaos of boarding, loading, last-minute changes that needs to stay on the ground. Off blocks is the last time to leave all these disturbances behind and revert to an unrushed flight SOP.
Uh.
Don't let the ground problems get airborne.
Okay, so pilots focus on managing themselves, their tasks, their pace. But what about technology? Are manufacturers building in safety nets to help catch these errors if they slip through the human checks?
Absolutely.
Yeah.
There's a recognition that even with the best procedures, errors can happen, especially under pressure. So, systems like the Takeoff Securing Pack, or TOS, are being implemented, particularly on modern fly-by-wire types like Airbus.
TOS Pack 1? What does it actually do?
It's essentially an automated cross-check. It runs a series of logic tests on the performance data the crew has entered into the FMS, comparing it against the aircraft's known state and limitations.
What kind of checks? Can you give examples?
Sure. It does a weight check. Is the zero fuel weight entered plausible for this aircraft type and configuration? It checks the V speeds. Are they in the correct order? V1, VR, V2. Are the speeds themselves reasonable given the weight, the thrust setting, the flap configuration?
Ah, so that would have flagged the massive error in case study 1 where the speeds were way too low for the config?
You'd expect it to, yes. It should detect that inconsistency. It also checks the stabilizer trim setting to catch potential errors in center of gravity input, and it verifies the temperature inputs, making sure the flex temp isn't abnormally high for the conditions, or that you haven't accidentally selected MCT, maximum continuous thrust, when you intended flex. It's a crucial digital backup.
So pulling all this together, the human strategies, the tech safety nets, what are the big lessons learned for crews trying to navigate this pre-departure minefield?
Well, a couple of key things stand out from the sources. First, reinforce crew briefings about phases needing a sterile cockpit environment, minimizing non-essential chat during critical data entry.
Makes sense.
Second, and this is vital, use common sense. Develop a feel for the rough order of magnitude of the numbers you're dealing with. Don't just blindly trust the computer output.
Can you give an example of that kind of gut check?
Sure, if you're flying a big bird, say an A340-500, on a really long flight, you just know your takeoff weight is going to be north of 300 tons. It has to be. Or conversely, if the FMS calculates a really high flex temperature, like 75 degrees Celsius,
That means very little thrust reduction.
right, which usually means a really light takeoff weight or a very long runway or both. So if you know you're heavy and you see a 75-degree flex temp pop up, alarm bells should ring. Something's wrong with the inputs.
That basic sanity check is crucial. And the final piece of advice, if things do go sideways.
If you know you've been distracted, if there's any doubt, especially after last-minute change runway, wait, whether the message is crystal clear, stop, take a breath, and redo the performance calculation from scratch. Use all the tools of the FMS, maybe backup paper charts, the laptop performance calculator if available. Double-check everything when things are quiet.
Better 10 minutes late on the ground?
Than arriving at a disaster on time. Absolutely.
What a powerful set of insights. It really underscores that managing the inevitable chaos is more critical than trying to prevent it entirely. It comes down to acknowledging human limits under pressure and having robust strategies.
It really does. Disruption is part of the job. And, the source even gives a nod to good old Ed Murphy. Anything that can go wrong will go wrong. Those small errors, they find their way in precisely when the pressure is highest.
Which brings us to our final thought for you, our listeners. In aviation, we've seen that when a tiny error can have potentially fatal outcomes, the safety rule is to slow down, segment tasks, and secure the data. So where in your life, your work, when the pressure is on, the emails are piling up, the phone's ringing, where do you need to apply that pilot's discipline? Where do you need to build in those small, secure task packages? And perhaps most importantly, when do you need to recognize that feeling rushed is the signal that you must, paradoxically, take your time and slow down? Something to think about. Thanks for joining us on the Deep Dive.